So we're moving into the second half of chapter 11. Mostly here I'm going to talk about causal models. Recapping, the big ideas in non-randomized design with respect to causality, you see relationship and then you say to yourself, is that relationship causal? And in the non-randomized design, in essence, the best pragmatically that you can do to examine causality is to control for variables that you think may be confounding variables, variables that may be affecting that initial relationship. And then several patterns of results might emerge within the subgroups. And I noted that controlling by forming subgroup categories is one way to control for effects of a third variable. The end of the text talks about multiple regression and other statistical techniques and procedures that do so. But basically speaking, suppose that within the subgroups the relationships remain intact and do so at about the same size of association as is the case in the full sample, that is to say prior to control. Well, then your basic conclusion is that the controlled for variable isn't a confounding variable after all. And you indeed may conclude that the relationship that you see prior to control is not due to that controlled for variable. You can't conclude that the relationship is causal because there might be another confounding variable which, if controlled for, would make the relationship go away. At the other extreme, you might control for your potential confounding variable, and indeed when you do so, the relationship within the subgroups disappears. And I said to you that in that situation, you basically conclude that the relationship is due to the confounding variable. Basic conclusion is that the initial relationship is not a causal one, because when you have eliminated the effects of the controlled for variable, the relationship is gone. That is, it's gone within the subgroups. But I said that the logic of the causal reasoning is more complex than just described. And I'm going to use causal models to demonstrate some of the nuances and complexity of that reasoning. Now, a causal model is basically a visual diagram of the factors that bring about a relationship. In a causal model, arrows convey the effects of one variable on another. To see the effects in these very simple models that I'm going to develop, what one does is trace along the arrow path or paths from one variable to another, going only in the direction that the arrows point. So the causal effect is in the direction of the pointing arrow. So in essence, there are different causal models, and we'll cover sort of two prototypes, but we're only getting a sampling of the complexity of this. An antecedent variable model is one in which an antecedent confounding variable directly affects two other variables, and by so doing generates relationship between them. In an antecedent model, neither variable in the initial relationship affects the other. So the antecedent variable brings about the relationship. If you don't know, antecedent means precedes in time. So here's an example of an antecedent variable model. Here the antecedent variable is low motivation, or we could simply, perhaps it would be better to call it motivation level. But the notion is that low motivation causes marijuana use. I mean, that's the direction of this causal effect. And low motivation also causes, as is conveyed by the straight arrow, poor grades. As this antecedent variable affects each of the variables that were in the initial relationship, it brings about a relationship between them. So if you did not control for motivation, you'd look at the data in the full sample and you would find relationship between marijuana use and grades. And you'd find that relationship even though neither of the variables in the initial relationship affected the other. So how do we know that in this model, for instance, marijuana use does not affect grades? Well, we know that because there's no arrow from marijuana use to poor grades. So this model is sort of, I think, perhaps the most common, or one of the very most common ones. I mean, this is one of the very basic ways that relationships get generated between variables, even though neither variable in the relationship affects the other. So here's the second causal model that we're going to look at. It's an intervening variable model. And in the intervening variable model, an intervening variable passes along, or we can say mediates, the effect of a first variable on a second one. So in this causal model, the idea is marijuana use has an effect, leads to lower motivation, and lower motivation in turn leads to poor grades. So I'm just going to leave this model up here just for a few seconds so you can take a look at it more prior to moving on to the next slide. So the question comes up with respect to our intervening variable model. Uses marijuana cause low grades? And it's tempting to say no. Now, it's tempting to say no because no arrow points directly from uses marijuana to low grades. Now, the correct conclusion in looking at the intervening variable model is that there is no direct effect, or we could say no direct causal effect of marijuana use on grades. And that's indeed because there is no arrow going directly from marijuana to grades. However, it's not correct to say that there is absolutely no causal relationship between marijuana use and grades. That's because in this intervening variable model, there is an indirect effect that mediates its way through the intervening variable, low motivation. So the question comes, is there a causal effect of marijuana use on grades in this intervening variable model? And the answer is yes, there is. There is an indirect causal effect. And then the question could come up, we could ask, is there a causal relationship? Which is to say, does one of the variables in our initial relationship affect the other? I mean, and basically we're looking at here, does marijuana use affect grades? And there is indeed causal relationship in the sense that there's indirect causal relationship. Uses marijuana, leads to low motivation, leads to low grades. There's an indirect effect and therefore an indirect causal relationship. On the other hand, there is no direct causal relationship. Here's one more look at our intervening variable model. And here's a look at the antecedent variable model. the one in which low motivation affects both marijuana use and generates poor grades. In our antecedent variable model, there is indeed no effect of marijuana use on grades. I mean, and you see that there's no effect because there's no arrows that trace an indirect path onto poor grades. I mean, there's no path here from marijuana use to motivation because the arrow is going in the opposite direction. So there's no indirect path. And also, as you can see, there's no direct path. There's no direct effect either. Which is the correct model? The intervening variable model or the antecedent one? Basically and pragmatically, from looking at the data alone, we don't know which of these is the correct model. And this is not an unusual circumstance. It's often the case that a researcher can't tell from their data which model is correct. Now, the model that is correct has some important implications. Before we go on to the next slide, let me just say that there are models other than the antecedent variable model and the intervening variable model that could also account for our data, and we're not going to discuss those, given that we've got just a quick introduction here. So I just mentioned that which model is correct can have important implications. So if the antecedent variable model is correct, then neither variable in the initial relationship is affecting the other, either directly or indirectly. So therefore there's no causal relationship whatsoever. On the other hand, if the intervening variable model is correct, then we've got if that's the correct model, I mean, that's telling us that there's no direct effect. It's also telling us, however, that there is an indirect effect. So there's no direct causal relationship, however, there is indeed causal relationship, that being indirect causal relationship. So the rub is often, almost always, we don't know definitively which model is correct. From a policy implication perspective, if the antecedent variable model is correct, one could argue, well, it doesn't make much sense to have a major initiative to stop marijuana use. That's because marijuana use isn't affecting grades, so I mean we don't think that we don't see reason to think that this would improve academic performance. Now one could argue there are other reasons why marijuana use should be reduced. But on the other hand, if our intervening variable model is correct, then the notion becomes, well, marijuana use is indeed leading to poorer grades. Therefore, from a policy perspective, let's really get in and do some things to discourage marijuana use. So the same ideas will come up oftentimes in social work services and planning of social work services. So the interpretation of the correct model and then the uncertainty of which model is correct can make planning social programs difficult and a task that has a great deal of uncertainty attached to it. So we're going to mention some issues pertaining to control for multiple variables. So we can indeed control for more than one variable at a time. And we can do so using tables, which is the technique we've used in the past two chapters. I mean, there are a couple of problems that emerge. The biggest problem is that the sample sizes in the subgroups become very, very small. And I mean, related to that, I mean, the number of subgroups becomes very, very large as you control for more and more variables. So tables become large and cumbersome. And I've already mentioned that there are some multivariate statistical procedures that control for many variables at the same time. Now, the fundamental problem in control for variables in non-randomized designs, as I've already mentioned several times, is that one can never control for all possible confounding variables. So at the risk of overgeneralizing, let's just say almost always in non-randomized designs, and let's encompass survey designs, because survey designs are clearly non-randomized. So almost always the researcher can have only limited confidence in areas pertaining to causality. Ultimately, and often the researcher is left to say, I don't know whether this relationship is due to A, indeed causal relationship and direct causal relationship on top of that, or B, due to a confounding variable, or C, due to both confounding variables and also causal effect. And then I could add D, and further the complexity of whether the model is more like an antecedent model or more like an intervening variable model further muddies the waters of causal reasoning. The point is that the researcher often doesn't know assuredly whether the relationship is causal. So that's not the same thing as being sure that the relationship is not causal. It's more, oftentimes, it's logically difficult to reach a conclusion about causality. One last mention, the randomized designs with random assignment to groups do away with confounding variables and create a situation where the researcher very, very often can have that high confidence. Well, to this point, we've covered 3 of the 4 patterns that I mentioned emerge when a confounding variable or a potential confounding variable is controlled for. Now, the 4th pattern was that the association within the subgroups varies. In other words, there's markedly different size of association in the different subgroups. And one of the names that is, in essence, attached to this pattern is that this is an example of an interaction effect. So in an interaction effect, the pattern of relationship between 2 variables differs according to the value of a third controlled for variable. So here's an example of interaction. And again, this is from the special needs adoption study. So we have 3 family ethnicity groups, and then we are looking at closeness of parent-child relationship for kids of different ages. So in essence, we're controlling for age at time of survey. And if we've got interaction effect, what we're going to see is different relationship in the subgroups. Let's start out and look at the relationship between age and parent-child closeness in minority interracial families. Now, the highest score possible here is a 4, and the lowest is a 1. For kids who are age birth to 5 at time of survey, the mean response is 3.52. I mean, so 3.52 is close to 4. So I mean, this is indicative of considerable closeness. But what we want to focus on here is our relationship within the minority and racial subgroup. And so what we see is that for kids 6 to 11, the level of closeness is quite similar to the birth to 5-year-old group. And further, where kids are 12 to 18 at the time of the survey, parents are still responding very positively. So these three mean scores, the mean scores for these three age groups, are so very close together that let's think of them as being the same. So in essence, the pattern of relationship that we're seeing for the minority interracial group is that there is indeed no relationship between age at survey and parent-child closeness. The mean scores do not vary according to age group. And certainly I just want to note that this is, I think, an unexpected pattern, that what one would imagine would be that there would be greater closeness between parent and child when kids were younger, and that closeness level would gradually decrease to some degree. Or at least I think that's what much developmental theory would say. So now, let's look at our white interracial group. Here you see a decline in closeness scores as age increases, from 3.66 to 3.35 down to 3.02 for kids in the oldest group. And this is indeed the very same pattern that we see for the transracial group, which, I mean, I note that it is smaller in numbers, but still we do see this same pattern. A decrease in parent-child closeness as age increases. And developmental theory, by the way, would say, well, this is the pattern that we'd expect to see. So this is interaction effect, because the pattern of relationship in these two groups, decrease with age, differs markedly from the pattern in this group, which is absence of association between age and closeness. So that's what's making this an interaction effect. The fact that the relationship within the subgroups differs. Again, here the relationship of closeness to age is that there is no relationship. And in these two groups we see a pronounced negative relationship between age and closeness. As age increases, the mean closeness scores decrease quite considerably. So that's interaction effect. Now let's contrast interaction effect with a situation, and this is hypothetical data, where we have association but not interaction. So let's look at the pattern within each of the three groups. So, and let me just mention that I've made this example such that the scores in the minority groups at all three ages are higher than those in the other two groups. So that overall there's a greater closeness in the minority group than in the other two. But that's not what interaction is about. Interaction is not about association. It's about different patterns of association in different groups. So here, in the minority group, our pattern is, as age goes up, mean closeness scores decrease. And that's exactly the same pattern that we see in the other two groups. So in all three groups, we see decreasing closeness as age increases. So we're seeing the same pattern of relationship between age and closeness in all three groups. So there's no interaction effect in this table. Now, the absence of interaction effect doesn't mean that we're not seeing association. I mean, we are seeing association. In all three groups, we're seeing negative association between age and closeness scores. Keep focused on this, and we'll compare to the prior table which has interaction. In all three groups, we see decreasing closeness as age increases. So in all three groups, we are indeed seeing association in all three groups. It's the same pattern of association. It's negative relationship in all three groups. Therefore, there's no interaction. Now we're returning to the real-world data, and here we're seeing absence of association between age and closeness in the minority group. On the other hand, we're seeing negative association between closeness and age in the white and transracial groups. So the pattern of association, negative association, in the white and transracial groups differs from the pattern in the minority groups, where there's no association. So it's this differing pattern of association in the subgroups that makes it such that there's interaction in this table and not in the one that we just looked at. Summarizing one more time, and hopefully not being too redundant, the most important things to take from the chapter. First is how difficult it can be to determine whether an association is causal, and indeed that confounding variables are the key reason why it's so difficult to reach conclusions about causality in non-randomized designs. And then further, do see indeed the real power of the designs with random assignment, that they eliminate confounding variables and greatly facilitate the drawing of causal conclusions. And I guess finally that all of this is simplified in the real world. Causality can be tricky, even in designs with random assignment. We are through the first half of the text, and most of our work now is going to shift to the domain of inferential statistics, and in particular the role of chance in relationships that are observed.